All right, good morning, everyone. As I get started here, first thing, I've got a couple questions in email that I was going to start with as I scroll past my scary-looking guy. And so the first question I got was on well, actually, all the questions were on ratios and rates. Um, so what I want to do here is I want to look at the question that was given to me and then look at rates and ratios in general. So the problem that we had a question this was 28 fifths equal to 112 xths, 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 112 x is on the bottom. And I think part of the problem is, hey, we have a variable down here. Now, I want to show the two ways that we have been looking at these things and what options can come out of it. In general, we learn a rule where we can say we can cross multiply. So, multiply across, and that's going to be equal to multiplying across in the other direction. And so this can be rewritten if I take all the red stuff, put it on one side, 28 times x, and I can make that equal to all the green stuff, which is 5 times 112. And that's cross multiplying. And that happens at any time we have an equality with ratios. Is the top of one side can be multiplied by the bottom of the other, and still equal the bottom of the first side times the top of the other. And so that's why I have these arrows here, and they make a cross. Specifically pre-Christian cross, actually, right? When the Romans, they were more like X's, not T's. And so we have this cross pattern. From there, we solve for x. And so we're going to divide both sides by 28. So divide by 28. Whatever I do to one side, I do to the other. And I have x equals 5 times 112 over 28. And at this point, my calculator can help me go through all this. Let me grab my calculator over here. And so 5 times 112 divided by 28 is 20. Now, cross multiplying came from somewhere. And so what I'm going to do is I'm going to show it the long way. Also, because remembering cross multiplication is not something that can always be done. So I did say I'd show it both ways. So what I'm going to do here, I'm going to rewrite the problem. 28 fifths over 112 divided by x, or 112 xths, whatever x ends up being. And I'll pull that up here. All right, so we did it there with cross multiplying. There's crazy guy. I'll scroll down there. We can clear fractions. And in general, when I have fractions, I tend to clear them. What I mean by clearing is I can take this whole thing and treat it as one unit. And I'll get rid of each fraction one at a time. So I'll start with the 5. So if I take the whole thing, I want to put big parentheses around it to show this step. And I want to multiply it by 5. And that means I have to do 5 to this side and 5 to this side. So the 5's here will cancel, leaving me with 28. Because that 5 here will cancel this 5 here. I'll do that in orange, my canceling in orange. That cancels that. But the 5 coming across here multiplies 5 times what I have sitting over there, 112 over x. But I still have a fraction, and I want to clear all my fractions. So what I want to do next is put parentheses around all of this. And I'll put that in orange for the orange step. And I want to multiply by the remaining fraction. So notice I'm multiplying by each fraction, and my fractions are going away as I do that. So here I'll multiply by x. So the x is going to have to go to each side of the equation. And for here, it's going to give me 28 times x is equal to, well, the x is on this other side here. When it comes across to here, is going to cancel, the one that's trying to come across. And that's going to leave me with the 5 times the 112 upstairs. And if I scroll back up, that puts me at the same place I was right here, right? When I have the 28x equals 5 times 112. I get to the same place. And so solving it from there ends up being the same thing. Alec asked, do you always multiply by the denominator to clear fractions? And I actually prefer the second way to cross multiplying. You'll find a lot of books teach you cross multiply, cross multiply. But when the equations can get a little odd, and I'll show you one here. What you can do is you can treat each fraction one at a time. And to answer Alex's question, yes, you multiply by each denominator one by one by one to get rid of fractions. So, whoops, I changed colors there by mistake. Let me make my 8 actually look like an 8. And so if I want to get rid of fractions here, I'll recopy everything down here. And I'll just take each denominator one at a time. So I'll start by multiplying by 3. And so the 3 has to go to each term. So for the first term, the 3's cancel. And that leaves me with a 1. For the second term, the 3 multiplies the x, and I get 3x over 4. And for the last term, the 3's upstairs multiply, and I get 9 over 8. But I still have fractions, so I'm going to continue to get rid of the fractions one by one. So I am going to multiply by 8. And the reason I did 8 was a multiple of 4. But even if I didn't notice that, I could multiply by 4. And then in one more step, I'd get rid of the fractions. But I noticed 8 was a multiple of 4. So this 8 has to multiply each term. So 8 times 1 is 8. Over here, the 8 cancels the 4, leaving 2. So 2 times 3 times x. And then over here, these 8's cancel, leaving me with 9. So I get 8 plus 6x equals 9, or 6x equals 1 when I subtract 8 from each side. And now I divide both sides by 6, and I get x is equal to 1/6. And so to answer Alex's question, yes, you do multiply by the denominators, and you can do them one at a time, and that will get rid of them. So you end up with something here that has no fractions. This is really, really useful when I can't cross multiply, when I don't have these combined as a singular fraction. And so I have a tendency not to cross multiply, like the book tells you to do right here. Cross multiply, but to focus on clearing the fractions from each side. All right. right, let's look at a couple of ratio and rate problems since the questions came up on these. Let me pull another one up here. And I think this is section 5.2 in the online book. Let me look at my print book here, 2 seconds. Still 5.2 in the printed book coming across. All right, so going to look at the problem. X divided by 8 equals 9 divided by 6. Now, cross multiplying gives me, for my first side, x times 6, or we'll write 6x, equals eight times 9. And I will divide both sides by 6 so that I get x is equal to 8 times 9 divided by 6, which my calculator will nicely give me. That's 72 divided by 6, which is 12. And so cross multiplication gets us out of our ditch there. Now notice in this problem, our variable was upstairs, which is kind of where we like to see it. Let's do another one here. Where I'm going to have 6/11 equals 12 divided by n. If I can get back to my thing here. 6/11 equals 12 divided by n. There it is. 6/11 equals 12 divided by n. Now again, I'm going to cross multiply this way, which gives me 6 times n is equal to multiplying this way, which gives me 11 times 12. I'll divide both sides by 6. And so I get n equals 11 times 12 divided by 6, which a calculator could work through. I'm going to cancel these two out. I'm going to get 11 times 2 equals 22. But again, when you get this, you can go right to your calculator. Just remember your order of operations. And so those were my general questions that I received on the ratio and rate problems coming across. Does anyone have any other questions on the homework or ratio and rates? And Janine said cross multiplying is cooler. I do think cross multiplying is cooler. You'll find once we throw in additions and subtractions that it gets a little more subtle. You have to get a common denominator, which is why I do the other method almost all the time now. When you get things where you have a fraction equals a fraction, cross multiplying works right out the door. As things get more complex, that doesn't come up as often as before. And so you find the habits that work for the problems you have. All right. So that was the questions we have coming up. We're going to kind of finish what's chapter 11 in the online and chapter 8 in the printed book. I do want to kind of see if I can look at, I'm going to try to add this here. This might get a little meta as I'm trying to add my web browser so I can show you something. So let me see if I can add my web browser here. Where is it? Apologize for me talking over top of everything. What is it called? That's not that. It's not. Is it that? Nope. 2 seconds. My apologies. Oh, there it is. All right. All right. And so you should see this. And this is on Blackboard. And what I want to show you on Blackboard is, one, I have the PowerPoint lecture slides, and I'm putting up all the chapters. I'll be done with that tonight. Unfortunately, the way Blackboard is structured, I'm not finding a way I can dump all the files at once. I have to build it page by page by page. But what happens in there is the lecture slides for each chapter in they're numbered on the online version coming across. Chapters 1 through 5 or 1 through 6 are the same. Chapters 7, 8, 9, 10, and 11 in the printed book are different on the online, and I will make notes of that. Notice I have chapter 1 online and printed here. When the chapter numbers change, I'll have chapter 11 online and 7 printed is what the title will look like. So it'll show the difference between the book. What I'm also going to be adding up there are all of the worksheets we were doing in class as a way of looking at the information that we could possibly have. Here's the meta bit, right? You can see me seeing you with the chat over here. I knew this weird meta would come across. So let me get back to here. And so that is where these are going to be, all in the PowerPoint lectures and slides. Underneath that, in fact, I'll create the space for it now, will be the worksheets. And so there will be an in-class for the practice worksheets. I'll put all of those up. Now, I'm probably going to rename this, but what I have here is a running schedule. And each time I do a video lecture, I put the link up here so that you can get back to the videos. YouTube does record them. You're able to go with them. And then also the due dates that you should be watching the first lecture, due to have watched it by today. The lecture we did on Thursday, due to watch on Wednesday. Sorry, Monday, Wednesday. I always do that. To watch this Wednesday. And then in what we're talking about today, due to watch next Monday. So I have the due dates to watch. There's a practice exam that is on word problems, chapters 1 through 8 in the book. It has 70 questions on it. The actual exam will only have 15, and it will be due on April 11th. And so the real exam, 15 questions, due April 11th. And these are all on, let me add a note here, on Pearson. And I'll submit that through. And so that's called the running schedule. And I'll keep adding things to that as they come across. All right. So I wanted to make sure you saw that. I'll probably send another announcement that I'm putting material there. I also, if I record any examples of a problem, I will put them in near the lecture. So today we're talking about solving expressions, any examples I do for solving expressions I would list underneath here. The other thing you can look at, and let's see if I can do this without going horribly meta, is I want to go, this is where the stream's actually going. Let me go here to my actual YouTube channel. My YouTube channel is public. Don't mind all the weird stuff that I get sent. So there's us live now, and here's all the things I'm recording for different classes as I record them. Yeah, pretty much everything's public, so you can watch the videos of the kids playing instruments or whatnot. But I have a section called MWCC classes, and I'm putting things up by the course number and the information that we're talking about. So you'll also be able to access those, and I will put a link here to the playlist itself. Let me make sure that works. Yes, perfect. Sorry, I'm getting used to all this. I'll come back here and link to all my MWCC recorded material. And so I hope to have all the resources in one place. Now notice, while I'm looking at a web page, I cannot see your chats. I do apologize if I'm... And that is now there. All right. So I'm going to close some extra windows and make sure. All right. So I'll come back here and I'll get it off of my web browser. And luckily you saw none of my horrible channels, which are actually none. All right. So I'll come back to my Blackboard and get ready to start. We're going to be finishing up talking about algebraic expressions. We've learned, and I really want to talk about the progression we're doing here, because I do think it's important to put these things in order. We learned arithmetic. Arithmetic, that's probably an E, I never remember. Arithmetic, yeah, arithmetic, which was addition, subtraction, multiplication, division, powers. I don't know how to write powers, so I'll just say some base to a power. And our grouping symbols. These all define how we combine quantities and numbers. And we learned it for different types of numbers, but we ended up with real numbers. And that really is the focus of chapter 8, which we're finishing out now, which is real numbers and algebraic expressions. And so we learned all the things that we want to start doing with this. I mean, we haven't learned, square roots yet, or roots, but they're the opposite of these things, just like these were opposites of each other. So we have a basis for manipulating quantities. And then we focused on word problems, which is what you guys are getting ready to be examined on. Not handwriting. Yeah, let's see, word problems. And that is taking reality and measuring it, putting a number to it, putting a quantity to it. And there's a lot of focus on and it really is kind of how English is odd, how we say our subtractions backwards, 3 taken away from 7, right? Well, 7 minus 3, or 3 less than 7, right? This whole, we say things not in the order we write them or do them. And in that process, we started talking about the idea of unknown things. Which the algebraic concept of the letter X, from Alchin, the unknown thing, translated back into Spanish, Western culture, and then English. And so we're kind of transitioning right at the end here, where we're talking about algebraic expressions. And some of the last things in the word problems were, well, what happens when you have an unknown thing? And that moves us into algebra. And so we have this idea of things we can count, 1, 2, 3, to things we can measure, like pi, and different numbers. But we know exactly what they are. To we can now start talking about unknown things like 3y or 4x. And y links to something, and x links to something in reality. We just don't know what the number is. What we're going to do then is we're going to take a step away from reality, which take a step away from reality in the sense that we're going to examine the patterns of these unknown things. Like what happens when I have 3y plus 4x? Or what happens when I have, I'll put another, this is a spell, scroll down a bit, sorry. What happens when I have 4x plus 8x? Well, look, I have 8 of a thing and have 4 of the same thing. So I have 12 of those things. And so we're going to figure out what that type of patterning means. We're going to talk about what we started to talk about here a bit more, these things called terms, when they're separated by additions or subtractions. And we're going to start analyzing the patterns that come out of this. And that's what the rest of the course really focuses on, is the patterns that we can see in things when we don't know what the quantity was. In the end, which is why I started with it, it's all the rules that you have from arithmetic. Those properties of real numbers that we built up and used everything for, we can still apply when we don't know what the thing is. It means we have to treat it, I don't want to say differently. We have to pay attention to what we don't know. I think it's probably not the best human trait. Like we educate ourselves for what you know, what you know, what you know, what you know. But even Socrates, when seeing the Oracle of Delphi, and said that he knew nothing, and that we realized he was a wise man. What you don't know sometimes is more powerful than what you do know. And if you can put what you don't know in a box, surround it by all the things you do know, you start getting a picture of what that thing is that you don't know. That really is the trick of this level of mathematics, of algebra, is taking the thing you don't know and putting it in a box. And the box we tend to use when we talk about it is x, which is a variable. And so we take everything we don't know that we can call one quantity, and we call it a variable. And then we exploit what it can do. And so we have been making algebraic expressions. We've looked at algebraic expressions and terms, and we've identified terms in algebraic expressions. Sorry, I keep hitting my pop filter if you hear that noise with my headphone, because I don't know where my headphones are. And so and we added some definitions. We had the coefficient, which is the number out front, and the variable. We had constants, and we had variable expressions. And those will be on the slides. They're chapter 11.4, 11.5, where we looked at that. What we're going to do now is we're going to look at the pattern of terms when we have variables. All right. And am I still, yep, I'm still on this screen. Let me move over to here. And come back here. Make sure I'm still getting good. All right. I've lost a class last week. The stream went down. So you're going to hear me pause every now and again. I keep checking the stream health, which is something that I have in my browser, and it basically pings back and forth to YouTube so that they can make sure that I don't lose you all. And if we do lose connection or whatnot, if you come back to the live link, it should pick up from there. If you have any problems from that, we will work it out. All right, so what we have here is like terms. This is the definition we're going on. We've talked about terms. And so each variable term of an algebraic system is said to have the numerical coefficient. So if we look at this term here, 3y has a coefficient of 3. And the term negative 4y has a coefficient of negative 4 for some reason. There we go. Certain visuals on my computer don't come across in probably because of my Linux nature, Linux operating system. Okay, so 3y has a coefficient of 3 because it's the number in front of it. Negative 4y has a coefficient of negative 4. Plain y has a coefficient of 1. And negative y has a coefficient of negative 1. And we discussed this when we were looking at coefficients. So let me put a couple terms up here, and we'll look at the variables and the terms. So let me switch back to my Blackboard. And what we want to look at is, let me change colors here, 7a plus 6b. Now notice the named portion is different. These have different variables. And we can think about it as A is something, right? And for right now, let's say A is apples, right? I'm going to use words that have the same first letter. So B is bananas. Well, if I have 7 apples plus 6 bananas, that's the best I can do. I can't combine them together. I might say I have 13 pieces of fruit, but that's not what the variables are saying. They're saying apples and bananas. And so I can't do anything with these differently named variables. This is a simple or a simplified expression. All right, well, let's contrast that. Let's compare and contrast with another expression. N minus 9n. And so what will we make n? Let's see. Do I know any fruits that begin with an n? Keeping it in the fruit term. I don't. One will probably come to me later. So I'll say nickels. Well, it's kind of hard, but notice I'm counting the same thing. So I have 1 minus 9. I can simplify this because the names are the same. Overall, I have minus 8 nickels, right? Spent too much money on Swedish goldfish at the candy store. And so I owe the grocer 8 nickels. But when the variables terms are exactly the same, we call that like terms. And when we put them together, we call that combining like terms. because we are counting the same type of unknown thing, we can combine them together. But it has to be exactly the same. The variables have to be exactly the same. So I'm going to do another example here and we're going to contrast and compare. Contrast and compare, different ways of doing it. So our first comparison, we're comparing apples and bananas, A and B, and we can't blend them together. And so the most simplified we can write it is 7A plus 6B. Now when I look at nickels, or n's, when the variable is the same, I can combine them. And combining them, this is my simplified expression. All right. Let's do another one here. 3x squared plus x. Now, the names are the same. We have the same variable. But this one is squared, and this one isn't. And so this is like writing 3 times x plus x. And we have this extra bit here that we have no way of blending across. We will find there are ways we can manipulate this to get useful quantities out of it as we go on. But in general, we want to say that x squared is not the same as x. And so this is simplified. Another way of looking at that is, let's say that I'm measuring lengths. Right, so I have something that has a length L times L, and let's say I'm measuring it in feet. Well, square feet is not the same as regular feet, and these wouldn't be able to combine. And so these kind of what seem like arbitrary rules in the inside of algebraic quantities do have a basis in reality. We kind of need to think of the unit needs to be the same for things to add. So we need to be measuring the exact same type of thing with our variables. And since we don't know what the variable is, they have to have the same power and the same name. And so in this case, the powers are different, so I can't simplify it. And of course, I'm going to contrast that with an example with powers where we can blend them together. 2a squared times b minus 2a squared times b. Now, the entire name of the term, and we can think of all of the letters that make up the term, make up the name, is exactly the same. So I have 2a squared b's minus 2a squared b's. Well, 2 minus 2 is 0. And this simplifies to 0. Well, we don't actually want to check this one. So let's say a equals 1 and b equals 2. I'm going to plug those into here. So I get 2 times 1 squared, right? Because I'm plugging the 1 into here, times 2 for the plugging the 2 into b, minus 2 times 1 squared, right? Because I'm plugging that into there, times 2. So 1 squared is 1, and so 2 times 1 times 2 is 4. 1 squared is 1, so 2 times 1 times 2 is 4, and 4 minus 4 is 0. All right, well, maybe I just picked the right numbers. So let's try something else. Let's say A equals 5 and B equals 3. So 2 times 5 squared times 3. Right, because I have my first 2. I put 5 into the A squared, and I put 3 into B. Minus 2 times 5 squared times 3. Well, 2 times 25 times 3 minus 2 times 25 times 3, or 50 times 3 minus 50 times 3, or 150 minus 150 equals 0. So notice there's some powerful things that can happen here. If I collect the things with the same names, I might be able to find an answer or see something that's happening without needing to plug individual numbers in. And so this idea of simplifying or collecting terms will help us make our expression the most useful for us. In general, what we try to do is we gather all the like things together, so when we finally do measure A or B, or we finally solve for X, we don't have to calculate it over and over again. It's only mentioned once, right? And so the idea of simplifying is each named part of the term, sorry, as I adjust my screen here, each named part of the term should only be mentioned once. And so notice here, this name was mentioned twice. So I gather all the things together, and I'm saying how many of them I have. In this case, it happened to be 0. And we checked, hey, this works, right? Doing this and simplifying it down will always give me 0 in this particular case. All right. And what happens here is this joins up with distribution, which we've used before, but we can look at these. So I'm going to look at some examples, and we're going to focus on with variables distribution, which we used before. I've got to clean off my blackboard here, so give me 1 second. There we go. We'll go back up here. I really need like a theme music pinger at this point. All right. Right. Sorry, that takes me a second to clear chalkboards now, but whoops. And there we go. Yes, good. All right. I like it when things are working. I'm getting a little more adept with the technology. I'm probably going to be, right now I'm sitting at my dining room table, which has been taken over by everything. I'm going to try to get a standing desk and space some things apart. So right now I feel really cramped. In fact, here, I'll take a break as I switch things over here. Right. You've got my microphone, my books over in the corner there, my spare, my audio interface, my tablet, my coffee, my larger monitor, right? So, there. The drinks cupboard isn't mine. Well, the Kahlua is. Kahlua and cream is mine, but anyway. All right, I'll put that back there. Yeah, we're not going to do this too often, but I need to clean up the area a bit, and definitely stand, not sit. This sitting is not going well. All right, so what I want to do is I want to look at distribution and how it relates to variables. So the property of real numbers we're going to look at is the distribution property. And we haven't used it as much as it helps out with what's happening now. And so we say if I have some number times a grouping of an addition. So notice there's a combination of multiplication and addition. It's the same as adding. And this gets distributed to each term. Now this came about, let me draw here. If I have a rectangle of B and C on the length and A on the width here, I could add the area of A times B plus the area. So let me draw this one orange and this one blue. And I could say that my orange, the area of the orange rectangle is A times B, and I can add to it the area of the blue rectangle, which is A times C, right? The area of this rectangle times the area of this rectangle. Well, that all ends up equaling the area of the whole thing, which is A times this length, which is B plus C. And that's where this distribution property comes from. The idea of distribution comes from the idea of building the areas of a rectangle. And I know we talked about this a couple times, but we haven't used it much. It does come in very useful when dealing with variables. So I'll start with what we just did with a like term. And I'm going to use the exact a squared b minus 2a squared b. And I'm going to think about this as the answer on this side. Now notice those are the exact same things. I'm just going to focus on the variable portion though. Well, that's not, notice these are the exact same things. Well, the exact same thing started on the outside. So I'll take the a squared b and I'll leave them on the outside. All right, exact same thing, exact same thing, exact same thing, exact same thing. Well, they started on the outside. That leaves me with 2 minus 2 on the inside. And we know 2 minus 2 is 0, and 0 times a squared b equals 0. So what we're doing in collecting like terms works because of this distribution property. Let me show you an example with one variable. Four x plus 5x. I have the same name thing. So that was like my a. So I can bring the x outside, and I have 4 plus 5, or 9x. It's the same as adding up how many x's I have. Notice, I'm going to scroll up here. The same part I had down here was the x's. And the same's come out front. My same part was the x's. The same part comes out front. And I'm left with the 4 plus 5. So this idea of collecting like terms, we can say is using the distribution property. It comes from our property of real numbers. All right, well, there's two ways this manifests itself. We can see an expression where we're combining variables together and we don't know what the answer is. If my order of operations was, hey, do the things in the parentheses first, then I'm going to multiply it by 2. but I don't know the value of the things in the parentheses first. I can't do anything with it. But the distribution property comes to save me, and I can distribute the 2 to each part, and that gives me 2x plus 2y. And now, one of the games we'll find is, putting x's in one place, putting y's in another place, getting all the things with the same names together. And so if I have liberated these from the parentheses, they've broken out of that cage. And now I can manipulate them however needs to be. And so the distribution property helps us do that. All right, and we can also see it. Change my color here. When we have the variable. And we could say this is 3n plus 7n. Though for me, because I can do that addition first, well, it's 10n. And that's what happens when I put these together, is 10n. With all of these properties, they are reversible. I can go from having distributed something to reversing the distribution. All right, I'm going to do some examples of simplification, and then we'll look at some different algebraic expressions. So if I have 2x plus 6x, if I simplify this, what does it equal? Well, I don't know what x is, but how many x's do I have altogether? 2 and 6, I have 8 x's. And that's what we mean by simplifying an expression. I still don't know what number is there, but I have it in a format that's going to be easier to calculate when I find it out. All right. And I'll do another one here. Which, I'm sorry, I'm going to keep changing colors as I change different examples. So 6y minus y minus 5. Well, I have 6 y's, and I take away a y, then I take away the number 5. Well, 6 y's take away 1 y is 5y. But the number 5, I don't know how many numbers are in y, so I have to leave that term there. And so this is my simplified answer for that one. All right. Figure out how many of the named things I have, and figure out how many of the constants I have, and put them over there. And this becomes our pattern for simplifying. All right. Let's look at that distribution property in slightly more complex examples. Kind of working through the examples that the book demonstrates in this section. I'll do yellow. This is an algebraic expression. I have something that's being multiplied by a term in parentheses. And then I'm subtracting from that answer 4. But we're going to use our distribution property. So I'm going to put 2 arrows coming out. This has to get multiplied here. And it has to get multiplied here to this term. When I do those multiplications, I'll be able to simplify it. So 1/2 times x. Now, I don't know what x is, so that's the best I can write that first term. 1/2 times x is 1/2 times x. But 1/2 times 8 is 4. Right? So I do this multiplication, it gives me this first term. I do this multiplication, and it gives me this second term. Now this -4 out here on the end doesn't do anything, right? Because it's not being multiplied by the half, it's there waiting. But look what happens. I have 1/2 x, that can't combine with anything else, but I have 4 take away 4. Well, that's 0. And this whole thing simplifies to 1/2 x. Now here's the important part of simplifying. So I'm going to show you, hey, what if this was the amount of money that I get back from a purchase. We'll say something weird like that, right? There's something in there that x equals. And I'm going to say x equals 5. I'm going to measure x and I get 5. No, I'm going to use a larger number. I'll use 20. I want to really make this a pain to show. Well, I'm going to do it by putting that 20 back into here. So 1/2 20 plus 8 minus 4. Because I took the x and I plugged it into here. Now I do my order of operations and I get 28 and half of 28 is 14 and I get 10. And so if I use the expression as I had it, I'll get 10. But look what happens when I put it into its simplified form. One half of 20 is 10. And that's the point of simplification, of using these rules. We might not know what x is, but we can take the patterns and put it into the easiest format for us to calculate. And in this case, it is the 1/2 x becomes the easiest pattern to calculate. I got one more example, and then I'm going to look at a couple of the word problems that come out of this. And this is a common thing that happens, and I'm going to show it in two different ways. I'm going to show it in its basic form first, and then I'm going to make it slightly more complex. So I have a negative sign in front of an expression in parentheses. Now, a negative sign, when we put it in front of a number, was saying, hey, it's the opposite of 4. Right? If I want a number line and I have 4, its opposite was -4. Well, if I put a negative sign in front of -5, right, here's -5, its opposite was +5. And we went, well, you know what? It's the same as multiplying by a -1, because a negative times a negative is a positive. A negative times a positive is a negative. We can think of this as multiplying a -1 in front of my quantity. So this distributes to the first term and to the second term. And so for the first term, I get -1 times 2y, and then I get minus I'll use it plus -1 times -5. Or I get, this should be a multiplication sign. Let me make my dot bigger. Let me make my dot bigger there. And so I get -2y plus 5. One way to look at it, when I see a negative out here, the signs change on each term. So this was positive, it became negative. This was negative, it became positive. And that's how I tend to do that, is I change the signs of what's in there. Well, let's look at how this actually shows up more often than not. I have 5 minus everything in a quantity. So I'm going to distribute this minus sign into both things. Now I'm going to do it by changing the sign. So the negative gives me negative 6x. Negative times negative gives me a positive. I only have one instance of the variable. It's negative 6x. So I'll put that out front. And I have a 5 and a 10. So that gives me 15. And this is how we tend to see it, is we'll subtract some quantity in parentheses, and that negative sign needs to be distributed also, so that we get our simplified form like this. Oh, textbooks are written at really odd times. All right. So Janine, you said you didn't get to write the last one. Did I put it off the screen here? Yeah. Trying to get back to it, and it's not sticking for me here. Oh, that's why. Be right there, Janine. Sorry about that. I didn't mean to scroll up. There you go. All right, and so this takes us through the end of chapter 11 on the online and the end of chapter 8 in the book. The rest of the course will be focusing on 9, 10, and 11. I will be putting the exam up, even though it's due in 2 weeks. That takes us up, that does all the word problems. I have a practice exam up there, and you will be able to practice that as often as possible. I'm going to get all the PowerPoint lectures up there, and all the worksheets we would have done in class are going to be up there. Remember, our class time usually around 11:30, quarter to 12. We stopped and we started working on the worksheets so you could have questions coming through. And so this is about the right lecture time. I always feel it's a little short because I don't get that interaction afterwards. But please continue to email me, and I'll try to either bring into the next lecture or record separately any questions you have. So at this point in time, I'm going to ask, do you have any questions right now? And for the people that asked the questions on the ratios, if I didn't answer the ones you had in particular, I tried to use what you had emailed me from Pearson. Please email me more details and I'll record some separate videos. Now, because I am speaking, I'm going to do this evil thing. Hi. Sorry, I don't like this. Personal thing, right? Need a shave. I don't know, should I do like an NHL beard for this? All right, so I'll just leave it here with any questions. When you're done, you can pop out a chat. I will end the stream in about 10 minutes if I don't get any questions. Yeah, visual clues aren't that good. But I don't know what to do when I end the stream. I've got a lava lamp that we just dug out of the corner. What I might do is I could just put a camera on the lava lamp so that there's motion, so that you know the stream's still alive. And that way when I need to blab or whatnot, you can just watch the lava lamp go. Oh yeah, I know I'm not supposed to be touching my face per se, but I'm literally going to go wash my hands when I'm done here. So I have this bad chin habit I've noticed. I'm working on stopping that. So I've got 11:35 on my clock. At 11:40, I'm going to shut out the stream. I'll answer any questions in chat. Until then, I will put up. Let's see if I can find a happy thing to put up. I'll make a happy thing. All right, we can always make happiness. So let's make a happy. All right. There we go. There we go. There's the happy shot. Everyone be safe and be well, okay?